各位老师、各位同学，欢迎大家来到北京工业大学节奏物理研究所子评论坛。我们今天非常高兴呢，能够为大家举办这样一个活动。我们的活动名字叫拓扑流体动力学基础讲习班。我们荣幸的邀请到 Renzo Ricca 教授为我们进行这个活动。在之前的15个小时当中呢，我们听Renzo Ricca 教授为我们介绍了许多拓扑流体动力学方面的基础知识。那么接下来呢，他将给我们做1小时的前言报告。本次活动呢是受北京工业大学2018聘请海外专家来校为研究生授课项目专项经费，以及中国国家自然科学基金 NSFC 支持。Renzo Ricca 教授呢是意大利米兰比科卡大学教授，他的科研领域是拓扑流体力学，他是剑桥学派代表人物，已发表 SCI 论文70余篇，包括独立作者 Nature 1篇，主编学术专著2部，综述性论文多篇，引用1486次 H 指数20。他是英美国家自然科学基金、英国工程与物理科学基金评审人，欧盟大型开放项目监督协调人，希腊国家科技部高级发展顾问， Springer 世界图书、帝国理工等学术出版社专著类审稿人， Physical Review Letters 等著名期刊的审稿人，是 Scientific Reports 数学物理方向的编委，曾组织2个大型国际会议系列及12次国际学术研讨会，3次国际暑期学校，曾任剑桥大学、普林斯顿高等研究院、伦敦大学学院、巴黎高师等众多顶尖高校的访问教授。他学术声誉卓著，学术人脉宽广阔。下面呢，我们就请 Renzo Ricca 教授为我们做这个前言讲座。好，谢谢大家。
Well, thank you. Thank you very much. Thank you very much to everybody to be here. And special thanks, of course, go to my host, Professor Liu, who was incredibly active to organize everything. So you are very lucky to have him here. And also, of course, to Professor Wang, who kindly supported my visit for this lecture course and this talk. So we will talk about aspects that are related, of course, to what we've been seeing, and I can rely now on your knowledge of linking number, of certain properties of fluid systems, so no need to introduce much more. This talk is about, as you see, the combination of geometry and topology. We love geometry, we love topology, but sometimes there are little devils in geometry that play their part in dynamical systems. I'd like to talk about these devils. Of course, you know, sometimes a devil can be under the disguise of an angel, but sometimes not so. And so I will talk about these two aspects. One, the angelic form of this demon, and the other one, the more devilish form of this demon. Well, topological dynamics deals with a number of issues that are of interest to us. Of course, topological quantum field theory has roots in work of Witten and developed since the 90s to modern time. And meanwhile, a resurgence of interest in the classical field theory, where we can investigate the structures that are inducing a field, like a magnetic or a vortex structure, or the induced field itself. And then applications. Of course, applications are very important, and this is just a picture from a real phenomenon that occurs every second that we speak. These are just plasma loops from the solar surface. So maybe I'll show you a little video as the seminar progresses. But these are pictures available on internet easily. Now these are just domains of research where topological techniques combined with geometric techniques are important because they may help us to extract information about what? Well, ultimately about energy exchange and energy information in various forms. And we'd like to understand either if energy remains discretized at the fundamental level and helps us to distinguish properties of matter at the fundamental level, or if some conservation laws are prescribed, then if topology and geometry helps us to understand the transfer of energy. And here is a picture to remind us that this transfer of energy is extremely important for life and for human beings. As I mentioned, demons, by definitions, may be angels or may be devilish in their actions. So I'll divide my talk in a part where the devil is in the form of an angel, and then a second part where the devil appears as a terrible character. So the angelic part is a topological interpretation of some dynamical properties. In this, being a seminar is rooted on recent work. And the aim is the following, is to say something through geometry and topology of a complex system. And now is, for young people, this word is fascinating, complexity. But for people a bit older, like me, this word, there is one well-known reference for complexity, and is turbulence. Turbulence may be not so fashionable to young people, but is a prototype of complexity. When you want to really mean something complex, think of turbulence. But this is too far for me, too difficult for me to handle, so I will think of a particular type of turbulence. I will think of these defects as little vortices, vortices in a superfluid. Superfluidity is perfect because it's really ideal fluid dynamics. Yesterday somebody asked me, well, what is the lifetime of a vortex in a condition of helium being superfluid? Well, there are estimates, and in neutron stars, on Earth, superfluid helium is a bit artificial. You have to go and produce it. You have to go to milli-Kelvin temperatures to have superfluidity. But in the universe, it's not so strange. Phenomenon is occurring mainly everywhere, and neutron stars are made of superfluid helium, and the typical rotation of a superfluid vortex is of the order of 100 million years. So you put in rotation a vortex, and it stays there for 100 millions. 2, 3, 4, 450 million years. It doesn't decay, it doesn't dissipate. So this is the context, that we are in the superfluid. And this is a box, a numerical box. And I think this picture is taken by a very old simulation done by Carlo Barenghi in Newcastle. And nowadays you have very sophisticated pictures of the same phenomenon, of vortices that are interacting and, of course, reconnecting, changing topology, and moving about, etc., etc. Now, I will focus on a particular topic here that is more geometric in character, but nevertheless has some topology in it, and is rather simple. So I will think of one filament, and then I will duel with many of them. But one filament in space, we have this triad that we met already, tangent, normal, and binormal to the filament. And the filament, if the vortex is a superfluid vortex, then this is really, really a filament, is as a curve, as close to a space curve as you can possibly imagine, right? So there is no structure. Vorticity is like a delta function, and either is vorticity on a space curve or there is none else. So this is my vortex. Now, being in such a context, such idealized context, I'm safe to say that vorticity is basically a constant you may think of equal 1 times the unit tangent. So this is like a vortex line, as a material line we mentioned before. And this is in ideal conditions, so circulation is constant. Now, I want to talk about these quantities that we didn't meet yet, linear momentum and angular momentum, but I want to approach them with a geometric approach. Linear momentum is, you may think of the impulse that the structure receives from some instantaneous action, and I consider it per unit density. Now, the definition from ideal fluid mechanics leads you to this form. So this is the classical fluid mechanics definition of linear momentum, and we have an equivalent one for angular momentum, where X, capital X, denotes the point, the material point on the vortex filament, and this volume, V, essentially is the length of the filament because the cross-section is basically so tiny. Now, anyway, I have to start from here because this is the information I have for classical vortices, so it's a volume integral. But because it's so thin, I can consider omega along the tangent and basically negligible contribution from the cross-section, so I come out with a circulation. Is the flux of vorticity through the cross-section. So the flux of vorticity through the cross-section is gamma, and gamma is conserved. And of course it's conserved in classical ideal fluid mechanics and in superfluidity. Actually, in superfluid, in quantum superfluids, this gamma is discretized through the Planck constant, and it takes discrete values. So you may think gamma equal to 1. So the linear momentum is reduced to this expression. Very, very simple. Problem, and similarly for the angular momentum. Problem is that you like to evaluate this expression. Very good to have it on books. But what about on a computer? You want to have a linear momentum of a system, a tangle of vortex lines that are moving. So evidently you have to perform an integration, and you have to know at each instant of time the position of your vortex, and you have to integrate over the length of the curve. And this is not an easy, straightforward business. You have to integrate over all the curves, and imagine that you have many, many of these curves. And these curves are changing topology and changing geometry continuously as the system evolves. So it's not so easy. Is any better way to do it? Maybe we can extract some information from these expressions, as I just shown you. Instead of computing helicity through the integral, you extract information from linking numbers. Same idea. Well, the idea indeed can be put in place if we observe here that x cross dl can be worked out. First thing, I just like to remind you that these quantities are invariants of ideal fluid mechanics. These quantities are invariants, so once we get some information here, we can work it out, and in time probably is preserved. Now, let's have a look of a single curve, and let's see if we can extract some information, and then we think of knots and links. So we start from this expression, we go there, and remember we came from here, right? So we are there, and we rewrite dl as dx, ds in ds, because dl is just an elementary contribution from the length of the link or knot we consider. And now we consider x dx, this term, x dx. Well, x dx you can prove that is an area. So you can show that actually this reduces to a surface integration. And this surface integration is on some area. Now, it's not a big problem if you think of a vortex ring, for example. A vortex ring. So you projected the ring on the plane, you have an area, and that is the contribution to the momentum. You compute the area, and there's no big problem. Now, the problem is that this area is the projected area, according to some direction of projection. So if, the momentum is a vector, has three components, if we want to understand each of these three components, we have to consider the decomposition along the three direction of projection, and we will have three different areas. And these areas will contribute each to the momentum. Now, similarly for the angular momentum, we consider the components, and for simplicity, imagine that these components are along x, y, z. Then we take our system, we project it along one direction, we will get information for the component along that direction. Problem is that if the curve projected gives you a curve that is a graph on a plane, so a planar graph. If the planar graph is simple, it has no self-intersection, is a graph of a convex region, then no problem. You compute the area, is the standard area. But what about if the projected curve is a standard graph? The graph type of graphs we have in graph theory. If the projected graph is a nodal curve, in other words, is a planar curve with intersection points. Okay, well, we have to be a little bit more elaborate on that, and we have to understand what is this area, the area for the graph. Now, first of all, notice that our curves are oriented because they inherit orientation from the vortex. And being oriented, that means that the graph will be made by oriented edges. Now, I will call this graph a lambda with a vector there to remind us that it's oriented. And I put an I to remember the fact that we projected the original curve along the I direction. So for each direction, I will have a different diagram. Now I want to consider the diagram, and I want to focus on this diagram. Now, whatever is the graph complexity, I will identify the regions. For example, in this case, I have a region R1, a region R2, and the region R3. These are called, in graph theory, faces. And these boundaries are called the edges of the graph. And the intersection points are the nodes of the graph. All right. But our edges come from a vortex. And with a vortex is associated a circulation. And so you start now thinking, well, you have a circulation of a fluid, and this is the fluid. And now you think of the action of this fluid going through each region. So each region that you see here has some area, standard area, is also pierced by field lines. But these field lines may contribute maybe a single linking, a single Gauss linking with this edge, but maybe the field lines associated with this green strand will pierce also this R1 region. So the linkage is due to each contribution, each coming from each point of the region, and each point of the region will be subject to the contribution of the linkage of streamlines from other strands. For example, the blue strand on this region red, and the blue strand here on this region, R1. Well, Professor Liu has been very kind to circulate a paper, that one that was sent to you by myself and Nipoti, on Gauss linking number. And the second part of that paper is devoted to prove the expression of the linking numbers in terms of algebraic countings, or algebraic signs, but there is another proof there of the same linking number in terms of what in topology is known as the index, intersection index. And here we have to compute this linking number through intersections. Intersections of what? Well, follow me. We have the following way to compute intersections. So remember, this point is any point of your choosing that is just the piercing of a streamline around the strand. But I can work out an index, an intersection index, that measure the linkage between streamlines and strands through the following procedure. Take a point, any point you like, and take an arrow out any direction you like. Say rho hat. Rho hat is just a unit vector that indicates the direction of your choosing. And then you take the tangent, local tangent, at the point of intersection. Here, this little point there. Now you have a reference frame. And this reference frame is, you choose convention, tells you to choose a right-handed reference frame, and you count the crossing here of this radial direction with the strand. In this case, we have only one crossing, the little dot there. We may have different crossings, so we consider the intersection sites of the radius of the radial vector rho hat with all the diagram, with all the graph. And at each crossings, we prescribe an epsilon value, plus or minus 1, according to the right-hand rule. Well, suppose that I consider the same point, exactly the same point, but I want to have my life more complicated. I don't want to choose the simplest possible choice I've shown you, but for a pedagogical reason, I want to go through a number of strands, okay? I said at the beginning, any point in any direction rho. So I take the same point, but I go in a different direction. In a different direction, maybe this direction. In this direction, I meet 3 intersection points. 3 intersection points. With the blue one, with the blue curve, I still have the contribution I had before, because it's the same, exactly the same direction. Same as here, so I have a +1 and another +1, but I have a -1 in this direction, if you consider the right-hand system at each intersection point. The resulting index is the intersection index. And this intersection index, which is +1 for this region, is the same index of any point belonging in the region to the region R1. So I repeat, you pick any point you like, you go in any direction you like, you compute with this formula your intersections, you sum up the intersections, and you come up with an index. This index is a topological quantity, is a topological invariant of each point of the region. In other words, the index, being the linking number, is a topological invariant of the region. Is a linking number because you give interpretation in terms of linkage of streamlines with that region. Okay, so you call this index, say, intersection index. At some point, originally, I wrote a paper on this, and I call it Cauchy index. And somebody thought that I got the idea from Cauchy, and I am happy to say that I didn't. But I gave Cauchy some credit, because I think has to do with a Cauchy evaluation of singular integral. Let's leave it aside. But it's nothing to do with Cauchy. It's just a way to pay tribute to so many contributions of Cauchy. Now, of course, we can calculate this index for each region. So we give a +1 to this region. What about this region? Well, it happens to have a +1. And what about the third region? Well, the third region is this. You pick a point there. You choose the simplest possible intersections are 2 there. You count and you get to 2. So you now are doing the following. You are now thinking that each area being subject to a contribution of streamlines can be interpreted with a weight. There is a measure of the area that we know is a standard area, so a geometric measure, plus this measure has to be weighted according to the index. So we come up with the idea of a weighted area, curly A, and this curly A is just the summation of each contribution Aj, so the standard area of each region, each multiplied by its own index, intersection index. So we can come up with this solution that the linear momentum can be interpreted in terms of gamma times this area. And this can be applied to any complex graph we want, to any collection of filaments. So the purpose here is to not dwell too much on the mathematics, but to show you something of applications. So I give you some examples first. Here I have an example of a 4-crossing knot. The crossings are barely visible on the screen, but there's an overcrossing and undercrossing. It doesn't matter the knotting in this context, because I want to measure a linear momentum. Linear momentum cannot be related, we know, cannot be related to topology, has to be related with geometry. But I look at this picture. If I choose this orientation, I can work out my indices, and I use this picture to convey another message. That you see, there are areas with minuses, there are areas with pluses, and there are areas with zeros. If I'm going to multiply an area by the index, and the index is 0, it means it won't contribute to the momentum. So it can be a very large area, but with an index 0. Or it can be an extremely small area, but surrounded by so many strands that its weight might be, its intersection number might be very high number. So when you look at these areas, you start to think, well, first of all, it depends on the index. And then there is another thing, another bonus of this reading. This reading allows you to say, well, to distinguish regions with a plus from regions with a minus. Regions with a plus will go in the direction, say, that you like, and regions with a minus may go in the direction you don't like. In the opposite direction, I mean. Okay, what about this diagram? Well, this diagram is more or less what I just said. You have a big area. Here, you do not notice overcrossing, undercrossing. Why? Because this comes from a projection. It's already a graph. It's already a graph. You inherit the orientations, and then you compute the indices, and you have a large region that is 0. And then you have surrounded by regions plus minus. Plus minus meaning that these regions around maybe are going one way and the other. One is coming out the screen and the other is going down the screen. What about this stage? This stage maybe is an evolution of dynamical system, of the vortex you like, that has an area maybe small with +1, and lots of areas with -1. So this vortex, this particular vortex, would move contrary to the motion you expect, would move backwardly. We are accustomed to think of a vortex ring that moves in a given direction. and then you deform or you perturb this vortex ring, and this vortex ring forms coils, and maybe these coils start to turn a little bit, and if they turn in a certain way and they are consistently turned, like in the diagram shown, maybe it goes backward instead of forward.
Excuse me. How about change the direction of projection of field 8 now?
Sure. Everything changes. This is geometry.
But the total sum is the same. Total sum is unchanged.
Sure. Yeah. Okay. Now, the momenta for vortices of different circulation are, not so relevant for superfluidity, because in that case, I just mentioned, the circulation is equal for all these defects. But just in case, if we have different circulation, it would be nice to, sum up. So suppose that each vortex has its own circulation. Then suppose we have a link of this type. Then you think that this link determines, oriented link determines these indices, but then you still have a problem that circulation is not equal, and so the circulation being given the result of the piercing of the streamlines contribute differently. So you introduce similarly a kind of weighted circulation, and you weigh the circulation at each crossing site. For example, here you see you have two crossing sites. At each crossing site, you consider the circulation that you inherit by the particular strand. So the blue strand is gamma 1. So at the first site, you will have a gamma 1. At the second site, you will have a gamma 2 contribution. So you average this contribution into a gamma bar, and then you apply the same idea. The same technique go through, so you can calculate the contribution to the linear and angular momenta also for a system of vortices with different circulations.
I'm sorry, what is J?
So J is
I guess it's K.
maybe no. J is just the average that you get from different Ks. When you sum over R, for example, here you have two strands that are contributing to this area, and so the area J has a gamma J circulation.
You're left with index of K instead of J. It's K, I guess.
Yeah, it's K. But we are not summing on K. We are summing on R.
So it's gamma bar J. It's gamma K bar, not gamma J bar. Yes? It's on the left-hand side.
Yes?
Gamma K bar, I guess.
No. You like to call it gamma K? Yeah, probably. Okay, fine. Because we sum on J several regions have a J. It's okay, but yeah, stick to J. Because we have several regions to count the gamma. Each region, this would be R1, R2, R3. We sum over these different regions. And each region will have a gamma that is not just the gamma kappa, but is the gamma associated with the average kappas. Because, for example, this region will be heated by this gamma and this gamma. Okay?
So gamma is circulation in an area.
This is a graph.
Yes. So what does gamma bar mean?
Is exactly what is written.
It's an area, in this area.
Is the summation of the contribution of these indices times each single circulation.
In each region.
In each region, yes. So this is a rather old, you see, 91 numerical experiment by RF and Zavascki. And this is, at the time, the best could be done to study reconnection, change of topology of interacting vortex rings. So they shot a vortex ring, elliptical shape, another vortex ring, one against the other. One was reaching the former and was interacting, reconnecting, at a certain place, say 2 location, and by reconnection, they were forming a link. The two strands separated. Now, if we take that picture and simplify the picture in the diagram, we would have this system. And with system, it would tell me that this region, which has its own area, has an index 2, so is likely to be shot away furthermore. But I cannot prove this work. I cannot have access to laboratory experiment, but I do have access to laboratory experiment for this example. This example is a beautiful representation of a beautiful example work done by Lim in Australia, in Sydney, again years ago. So you take a vortex ring, say you color it with blue ink, and you have a second vortex ring and you color it with red, for instance, or orange. And you let them collide. And these rings are exactly axisymmetric, so the linear momentum is 0. And so if you do the diagram and you don't know the result of the experiment, what you can predict? You can predict that there is a central region, 0 index, won't contribute to the momentum, and these indices, you work out the indices, and you will see that is 1, -1, +1, -1, +1 around, and through reconnection, you can understand that there are formation of small rings. Okay, the small rings will move different directions, and the structure will evanesce, will die out quickly. I'd like to show you 2 movies. Classical, water, Navier-Stokes. And I mentioned the difficulty to measure momentum for systems. I mentioned the fact that we'd like to have a method for knots and links, so I'm bound to start first with a movie of a vortex knot produced in water. And this is done by the group of William Irvine in Chicago. Let me see if I can get to the movie quickly. Okay, so this is the movie. So the movie will show you, this is a rigid, is a solid structure. Imagine that there is a piece of a wing, of an airfoil. You take a wing, a section, and then you make it small, like so. There's a little wing, so it has, the profile of a wing, and then you produce a knotted wing in the shape of a trefoil. And then what you do with this wing? Well, the wing has to move in the fluid. This is water. So you make it moving, you give it an impulse, momentum, to this wing, and the wing will leave behind a trace of little bubbles, tiny white bubbles, air bubbles. And the air bubble will go to the low pressure field that is left behind the wing. So is a way to visualize any vorticity, or the dominant vorticity. Of course, there is vorticity in the fluid. We said that. So let me go with the movie, and then I'll play it again, maybe. You can see that overcrossing, undercrossing, this is a real trefoil knot in water produced by laboratory experiment by William Irvine and his group in not long ago, 2013 maybe. And then dissipates, of course. There are lots of features interesting because we talked about topology a number of times. And where is topology? Well, clearly topology is conserved, but this is real fluid, water. So there is a time where the vortex strands, so to speak, or the strands of bubbles come together, close, and here, for example, if you pay attention here, at a certain point the two strands reconnect. Well, the reconnection problem and topology changes. You see, here is hard to visualize, but they compute the shape of this, and through analysis of the picture, you can go from a trefoil knot to a link, and then decays further. All right, so I'd like to show you Lim's experiment. This is, okay. So you see, head-on collision of colored vortex rings. This is the Reynolds number. Is a measure, as I said, of ratio of inertia and viscous effects. So the highest the number, the more close you are to ideal case. But if we go, there are videos, there are movies of higher Reynolds number, but the dynamics is so rapid that I prefer this one. And this, contrary to my, is if it works for this, it works even better for high Reynolds number, my strategy. Anyway, the formation of small rings, he says, note, from the cross-linking of the wavy vortex filaments of the large rings. So be prepared to see this. You have a shooting of two rings, different colors, they collide, and because the linear momentum is zero of the system, the only way the linear momentum can get dissipated and distributed is through a reconnection and formation of small rings. And when you see the small rings, on a computer is probably a bit clearer, you will recognize the motion of each ring made partly blue, partly red. They collide, and they form these rings, and you will see they are all wavy. Look at the, the laminar surface resulting from the collision. This is very important because it gives you a number of information, apart from being just a perturbation of the dynamics, but it gives you the information of how the rings, if we go higher in Reynolds number, if we go towards the ideal case, would eventually move. And you see there's wavy. And this waviness is just inherited of the fact that the rings tend to move away from the plane, compensating the linear momentum, plus and minus, plus and minus, plus and minus. Since we talked about reconnection, I'd like to show you some other video. Let me see if I put it here. This is a remarkable video that I was very fortunate. I'm sorry, the light probably make it difficult to see it, but is an experiment that done in Novosibirsk by the group of Alexienko, and he didn't have, unfortunately, the coverage of the first experiment on trefoil knot. Novosibirsk, in some sense, is remote from places where they publish, hits of science. And but I did my best to publicize this experiment because it is absolutely remarkable. And I was invited there very kindly to show me this work 2 years ago. So what you're going to see is, I won't tell you how it's produced because it's not so difficult to understand, but is a waste of time. But what you're going to see is a very close zoom up of a vortex filament, of one of the filaments you saw before. This is in water. And the close-up view of what? Of a vortex filament that is reconnecting with another vortex filament. It's the first time that we could see such an event with such a precision. Okay, so we go. Pay attention there. They become anti-parallel. They merge, and one ring is formed and the other is moved away. So this is a reconnection mechanism that makes topology changing. Pardon me? Well, this has to do with cavitation, yes. Indeed, the research is funded to study cavitation because, as you know, cavitation is an extremely important problem in propellers. Because for propellers, cavitation is damaging, is a damaging effect. So this is the reason why they carried out so much work there. But I don't think I'm putting them in trouble if I say that their real interest was reconnection of vortex filaments. So vortex dynamics. They are a group of people that are incredible, very, very good, and long, long work. So I show you again. You see here, vortices, they have a direction because it's vorticity, and they become anti-parallel. And when they are anti-parallel, the twist that we mentioned is so important. The understanding of how twist gets transferred during reconnection.
So the background flow is induced by this vortex?
Is?
Induced by this vortex?
Yes, well, yes. Background flow is, I want to be clear, background flow, they do all they can in order not to exert any, how to say, preferential forcing on the phenomenon, yeah. The geometry is a conical geometry. It's very interesting because they want to force the vortex pitch to go down one against the other. It's a bit complicated, the structure.
It seems to be quite homogeneous. The background.
Oh, sure. That's the purpose.
It's a surprise. But it's kind of surprising for me.
Ah, wait.
Maybe I'm wrong.
No, I don't want to say that the fluid is... What they want is to visualize the vortex. And then no, that's the point. That's the difficulty. They want to produce this reconnection in front of your eyes.
So they move their camera.
No,
So the flow.
that's the difficulty. They want to control the vortex, pitch the helix, so that at a certain point the strands reconnect and everything happens in front of you. So the bulk of the fluid moves, etc., but is like fixed in front of you.
My curious is what happened to the flow induced by the vortex when the vortexes are connecting.
Sure. Okay. Right. So it seems that when we think of Lim's experiment, we are not doing too badly because it seems to have some power, predictive power. This is the experiment. These are the rings, the small rings. And when you read the Nature paper, this is Nature 92, you see that they talk about the opposite movement of the relative movement of these nice small blue and red rings. Beautiful experiment. Now we are applying these ideas now to other types of a situation, and there is one that resembles the superfluid case, is the one that is controlled by the Gross-Pitayevsky equation. And this you can do some analysis on the basis of your code. So this is work done by Simone Zucker in Verona. So we simulated the evolution of a number of structures. Let's stick to this example that I showed you before. This just gives you the idea of time. As time progresses, there is a reconnection here, and then there is a secondary structure produced, and we could go up to this time for a third structure to be produced. So there's a sequence of reconnections leading to smaller and smaller structures. Now, Yeah.
What leads to the reconnection?
What leads to the reconnection?
There's no dissipation in principle.
Well, the easy answer, but I'm just joking, is that the two defects get close together, and as they close together, classically, not from the wave function viewpoint, you can explain that. Classically, you have a very simple explanation. You have an explanation. I give you an idea, which I do in my lecture course. But this is really not Gross-Pitayevsky's basic, very simple fluid mechanics. You assume that not at the reconnection side, but when they are approaching, then fluid is still ideal. And then you apply Bernoulli theorem. And then you can prove that in order to maximize the interaction, they have to go antiparallel. And then if you go farther down in the along with time, then you have to consider more finer analysis than what I've done. I think some analysis is currently done by Yoshi Fumikimura and Keith Moffat. They have a paper on JFM recently. They have two papers. And the last one appeared, I think, very recently, considering Berger's vortices with twist. And the first model, I think they didn't include Biot-Savart effects, and the second one has Biot-Savart effects. So is an open problem, reconnection.
Maybe I'm wrong. Maybe I try to propose another mechanism, so to speak. Gross-Pitayevsky, if we look at the transform to the fluid, then it's ideal fluid, but you have a pressure, a quantum pressure term, which you will introduce non-local effect.
Good.
But if we are looking at the older equation, the classical fluid, the vortex should not reconnect. Am I right?
That's right.
So in this case, we also have ideal fluid, but with a quantum pressure term, which is some actual non-local effect, then this term will lead to this reconnection. Is it right?
I have a different picture to propose you, but this is speculation. So, under speculation, this is my picture. We mentioned cavitation before. So now, there is for me, I'm pleased by the idea that these defects, remember, at the defect site, density is 0. Is exactly 0. So if you now do this exercise with me, just for pleasure, think of these as empty tubes, and they are sucked one another like two bubbles would be sucked. Now, if you imagine to have two tubes of air in a fluid, but push one against the other with a certain amount of impulse, so that they do collide, but they also leave one another out, then you may think that, okay, is ideal, but you have a reconnection. In that sense.
Can you remind me, is the vortex lines low pressure point also here?
That's right. Oh, sure. This is Gross-Pitayevsky. No Biot-Savart in this simulation. This is entirely Gross-Pitayevsky.
So the quantum pressure is also minimum here.
Absolutely 0. Of course, in vortex dynamics, we have vortices with with low pressure inside. But the way to interpret this mechanism in such an ideal situation for me is nice. So I don't know if the experts object, quantum people object, maybe, but it works for me.
So you said it's still open problem?
Yes, Yes. Yes. Okay, so we keep going, right? We have the area we can implement. This is just to show you that the method can be implemented and can be implemented to a rather complex situation. So you have this, you take a projection, you take a graph, and the graph can be far more difficult than here. You discover issues in numerics that are quite interesting. For example, there may be regions that form cusps, and so you have to evaluate the area of these regions, and if the cusps are present, many more, they may contribute to the area and to the problem, to the numerical accuracy. Anyway, I go fast here. You just extract one diagram, many diagrams, x, y, z, x, and y, z, for instance, at one time. You can implement that in time. And you extract your indices, you compute the areas here, you multiply each area by the index, you have the evaluation according to the index. If I visualize the index 0 with no color, you see maybe there are regions that are not contributing to the momentum, etc., etc. You can do this at a later time, same play, and then you end up with a movie. You end up with a movie, I don't have it, but you end up with a movie with an arrow, and this arrow and the intensity of the arrow tells you the direction of the momentum as the evolution progresses. So you can estimate regions of high turbulence from regions of low turbulence, regions where heat flow is important or not. That's right. Okay, similar things for work that we done earlier, reconnection of vortex rings, if you like, same thing. I don't want to dwell on this fact, the fact that momentum should be conserved. There are differences, you see, there are small differences, and this difference, 6%, etc., these differences go down if we increase the numerical box. We have evolution of torus knots, 2-3 knot, and the 2-5 knot. The knot, as it evolves, goes through a reconnection, and these reconnections form different topologies, of course, and this is one stage, just to show you, because we started with the trefoil knot, or this is the trefoil knot, I show you the 2-5 knot as well, because the knot we started with is highly symmetric, then we expected the momentum in this direction, and indeed we found this direction. This is the result. Again, we have ups and downs of this, and for this 2-5 knot, same situation, a bit ups and downs of that. The interesting thing is that these ups and downs go down as you enlarge the numerical box. So the question is now to apply to a grant, to have time access to a bigger machine. But we have already been made sure that these things are getting to be more small as we increase the box size. Well, I'm not interested in the momentum. I'm showing you how to use techniques that are not relying on analytical expression for the momentum. You don't have analytical expression for complicated knots. For example, the trefoil knot we saw before in the experiment. You can extract this information without any, just data analysis. And so, image analysis, I mean. And so this is quite nice. Okay. You see the title, Topological Catastrophe of a Möbius soap film. So we are in the part of the talk where devil plays the devil. Before was an angel geometry, but now the geometry can be devilish, and so of a soap film. Why soap film? Why soap film? Zypher surfaces are nice surfaces for knots and links. What kind these surfaces are? Well, these surfaces are, you know, you prescribe a knot, and you can identify a surface for any given knot. For any given knot. This surface will be the surface whose boundary is the knot. And this is a numerical artifact of this surface. So there are now algorithms that produce surfaces, in particular this one, Van Wyck. Of course, you may have a knot that has a surface that is non-orientable, like this. Yeah?
Is the surface defined unique always?
No. You have many, many surfaces. You have infinitely many surfaces. As you would have, suppose, let's do a simple example. I mentioned soap films. You take a circular boundary, which is a filament of a wire, and then you put it in a soap film solution. You take it out, and you have a laminar disc. And then, as everybody did when we were a kid, you blow into this laminar, but wait, you don't blow it so to form a ball. You stay with a surface that is just changing shape and growing. Each time of this growth identifies a single surface that would give you a Zipher surface. So you have infinitely many surfaces.
By uniqueness, I mean a different topological surface.
They are all topologically equivalent
Really? So it's unique. The surface is unique.
in topological sense.
Not.
Yes, sure. But some of these surfaces are non-orientable. So you need to have an orientable surface. Why? Because you may attach to this surface a physical meaning. For example, if the surface were a surface of velocity or a potential surface, you would like to have the same value from one side and to the other. Okay, if the surface is a potential surface, maybe it's a surface associated with the magnetic field. And if it were, then the potential vector would be identified by one of these surfaces. Here I just give you the trefoil knot in different shapes. It's the same trefoil knot. But in this configuration, this surface is orientable. So it would be a good surface for us, and is the definition of a Zipher surface, being an orientable surface for the knot. Now, the problem is that these surfaces emerge in a lab, if you like, as soap surfaces, soap films. So soap films are fun to play with. I'll be very brief now. Well, I put here a short history of studies. It's remarkably short considering the importance of this topic in analysis. Basically, half of mathematics is due to the work on calculus of variation or optimization problems. So we start with Euler-Lagrange plateau. We did experiments on these plateau surfaces, then Laplace as well. And we come to mathematics, pure mathematics. We have a Fields medal by Douglas, and then Radot, existence proofs of a given contour, and Courant himself. Courant worked on soap films and induced the students to play with soap films, to produce them. It's cheap. You go home, you put some soap liquid in water, and then you play with this. Of course, much more work going on now for material science, for lots of applications. I like to show you the picture of Courant himself playing with these wires, embedding the wires in the soap film. And here is a lady collaborating with him. And out of this, they wrote a paper for students to play with. And immediately he noticed that for a Mobius band, there was a problem. Mobius band is non-orientable. So here I get my problem. The problem is this, a folding problem. I posed to Francesca Maggioni. We tackled that with a combination of cosines and sines. And what we are doing here? I take a filament, now is a thick torus just for visualization purposes, time equals 0. And I want this filament to develop a coil. And as time progresses, through these equations, you develop a coil, and the coil keeps going until what in mathematics is called a double covering of the circle, like this. So we start from here, we get there. Now, what about the opposite direction? Suppose we take a filament, a piece of wire, we start from here, and we go backwards. We take the same center line, and then we go backward. Imagine, I stop here, imagine that you take this wire, you put it in a soap film, and you release it. And you just perturb it a little bit to get rid of troubles, and then it emerges a surface. What kind of surface you would get? Now, you know what you're going to, because it would be a circle. So the final end state, you know, is a planar disk. And the planar disk is orientable, is a two-sided surface. You know what surface you develop when you do this? You put it in water and you remove it, a Möbius band. A Möbius band is one-sided surface and is a continuous deformation from there to here. So,
Finally becomes oriented.
exactly. So at a certain point, I visited Cambridge and I told Keith, you know, I met this problem. This is amazing. It goes from non-orientable to orientable. He instantly, look at me, and a second later, half an hour later, he came from the city center with the liquid, soap liquid, and the bucket, and we put water, and we started to do experiment. But you can imagine how badly we were with our hands and with films. And he said, wow, this is very interesting, Renzo. We have to do some serious work here. So we went to somebody serious. Chair of mathematical physics in Cambridge is Ray Goldstein, my age, my friend. And so we were lucky because Ray really appreciated the idea, and he did a lot of work, actually. So first thing, they applied for money and they bought serious stuff. So camera, high-speed camera, all the possible high-tech stuff to do experiments.
There's a lady here who has money now.
Well, that's why the seminar. I'm trying to encourage her to put some money on one of the things we saw. And with mathematics and Mathematica, you can imagine, you can, for a small thickness, small width, you can follow, you can adjust these kinematics with one more parameter, you have a surface, and you can see that there is a problem at a certain point. There is a problem, there is a strange problem there. And so we wanted to investigate this problem. This problem, to make it short, has been investigated. Some mathematics came out. And indeed, as far as I know, is one of the instances, I'm not saying the only one, but the best I know is the only instance I know where catastrophe theory has an absolutely precise application. Because mathematically, we uncover the twisted cubic catastrophe. But before doing mathematics, I want to show you the experiment. So this is the standard Plateau experiment, and this is the work of Ray Goldstein lab. So I show you the movie. Problem with soap films are so beautiful to see, but so hard to show in a movie because they are transparent, and so it's very, very hard. But what you're going to see is this is a wire that is held by these two tools, and the wire is moved very slowly. And the camera takes thousands of frames per second. And then you analyze the instant of formation of this singularity. So there is an instant where somewhere the fluid has to reorganize itself. I'm going to show you this instant. So the movie is this one. And you have to pay attention at a certain point to the border. Somewhere, I'm not going to tell you where, first run, somewhere there will be something happening on the border. So the fluid evidently part of it goes towards the border, and the motion is just the idea that we are moving away. We are trying to moving out to a circle. Blum is a twisted loop locally, and is immediate. So why do we have this twisted loop? You know, it moves, and at a certain point, this is the hole, and the hole disappears. And there is a twisted loop coming out. Now, this twisted loop, of course, intrigued us, and this is the picture. This is fluid. And then we started to go back to the idea of Tate, if you like. So there is the fluid inside is touching the wire at some point. So it's called the plateau border. The plateau border is actually the place where the fluid touches the fiber. So we put a curve here, a red curve, and you have to look. You know, topology is conserved because there's nothing breaking up. But there is a transition of the surface. The topological character of the surface changes. The topology of the wire doesn't change. And so if you compute the linking number, you see that the linking number right is 1, twist is 1, and it jumps to 0 when it's a circle. And there is a change in linking number. And now I'm closing down my seminar with one picture that I had in mind for you. Oh, probably it's not a movie, it's a picture. This is our observation. And from laboratory experiment, I want to go to nature. And I want to go all the way, very wild, to nature. And the wildest I can go is the following. Take the picture, you rotate the picture, like so. And it's nice to think this as a surface, maybe of the sun. We talked about magnetic fields, and the fact that these magnetic fields are like elastic. And this is elastic because it's a fluid. It's a soap film, it's elastic fluid. And what about this? So this is the observation 2002 of a destabilization of a plasma loop. When there is twist, this is technically called the right master type 1 move in topology. And the two things are very reminiscent one another. Okay, very last thing is a little movie to close the seminar. I had to show this because students have to see sun in action. And so we talked about plasma loops. That is actually this stabilization of a rope, magnetic rope, or plasma rope, sorry. And this is the picture, the movie I wanted to show you. So there are a number of movies. This is already old, 7 years ago. But with modern satellites, you have these beautiful pictures of loops that are like arches. And this is slow motion, slow motion of sun activity. It's beautiful. Some explosions. Maybe you will see some mass ejection because sometimes there are flares. You see loops, if they reconnect, they open up and they go to space. And they go beyond the Earth, of course, and they interact with our magnetic field. Well, thank you very much for your patience and for your interest.
Excuse me, because we want to use up our time. Only one quick question.
The ladies first.
No.
Okay, I take it.
can sometime later explain this the soap film twist in the same framework of ideal fluid without any singularity.
It has been, it has, in ideal case.
Because the reason I ask this question is because whether it's bubble or soap film or droplet, the interface is not a mathematical discontinuity. It's a some transition layer from liquid to gas or gas to liquid. So that means we have finite thickness, which is the same word of a mainframe path. Okay, so of course I appreciate that we have a mathematical model to assume this is a perfect surface or film, whatever to do with this what we had in the past 4 days. But do we believe that when we twist these things from non-orientational to orientational, at a certain time probably we have to deal with this finite thickness? Do you believe so, or?
I think, well, first of all, in the case of the soap film, there in particular, we have a tension like in magnetic fields that, how to say, is provoking a terrible, is dynamically very important. So in a normal fluid, classical fluid, we don't have that. And so that is an ingredient, a force somehow. But in cases of forces present, then you enhance these transitions of twist of writhe to twist or vice versa, of twist to writhe. But in your case, if you drop also the forces acting, and if you think of a layer, of a thickness, etc., you have to think of the rearrangement within the layer of various contributions. That could matter.
I would like to propose a different following this problem. I will explain that conjecture explains that the helicity goes to the boundary of the final ring. So there's no similarity actually. It goes to the boundary.
Sure.
Oh, that's right.
Sure.
Okay.
Sure.
Okay.
Sure. It goes to the boundary. And we...
Your picture does not show that.
No, it shows that it goes to the boundary. But I don't think has been proven. So it remains a we wrote it as a conjecture at the end. Yes. It's a proceeding National Academy of Sciences, 2010. Goldstein. Yes.
All right, please join me to thank the speaker again.
Thank you.
A round of applause and listening.
Thank you very much.